This is the presentation, Enhanced Visualization of Production System Concepts and Simulation Data for the Smart Digital Factory. I'm Jim Wong, a Group Manager at Statler Hinkie. During this presentation, I'll describe visualization techniques we used to enhance understanding of production system analyses and operations research principles. This work was funded by the U.S. Air Force. Aircraft maintenance, repair, and overhaul, or MRO, ensures the continuing airworthiness of aircraft or aircraft parts. Aircraft MRO is extremely costly. The U.S. Air Force spends most of its life cycle costs to sustain versus acquire its aircraft. Efficient operations is essential, yet challenging because production system responses to control inputs are delayed, nonlinear, and interacting. We developed a whip flow planning tool to help production and engineering personnel explore the impact of possible disruptions and their mitigations. This tool uses discrete event simulation to project the effects of different control inputs, such as buffer sizes, induction rates, outages, and capacity adjustments, on system behaviors, such as input and output whip, part processing rates, and part transfer rates. In order for any decision support tool to be useful, users must understand and trust the tool's output. We address this issue by reporting the values of intermediate as well as final variables, so users can trace through how the final simulation outputs describing production system performance are computed from the inputs which describe assumptions and production control decisions. In the first version of this tool, we relied on color-coded Excel sheets to display these variable values for each process step and day. The sheet at top inputs deviations from nominal capacities for each step and day. In this example, 3 days of outages in red are followed by 3 days of increased capacity in green. The sheet below displays the number of parts processed for each step and day. Red cells show blockage rippling upstream and starvation rippling downstream. Other sheets show variables such as input and output whip, parts transferred, and buffer space availability. This data is voluminous, so detecting and interpreting significant patterns can be time-consuming. The whip flow tool displays graph arrays to enable efficient data review and interpretation. The top graph array shows how the expected or planned capacity varies over time for each process step. Red regions indicate periods of low capacity at a step, and green regions indicate days when capacity is higher than normal. The lower graph array shows the estimated number of parts processed over time by each step. Additional graph arrays show other variables so users can understand more deeply the dynamics of the whip flow. The arrays are synchronized and can be scrolled and zoomed simultaneously. The tool also uses bar graphs to show a complementary view of this data. Each bar graph shows the values of a particular variable for each process step. Users can request an animation that advances from day to day automatically, or the user can press forward and back buttons to sequence manually through the data day by day. We developed a version of the Diagnostic-Tree, originally designed by Hopp and Spearman, to make operations research findings more accessible to practitioners. The D-Tree is a knowledge database comprised of nodes that each describe a possible production improvement objective. This screen shows the node for optimizing batch size. Our D-Tree provides an interactive listing of the nodes in the hierarchy. From any node in this list, users can navigate to the node's full description. We added a capability which we call Estimators, which displays the value of a node's objective from user-specified sub-objective values. The left dialog prompts the user for values of the sub-objectives, and the right graph shows how the objective variable varies with the range variable, in this case, sequential process batch size.